Hello and welcome to Chapter 7. Chapter 7 is Techniques of Integration. And what we're going to be learning is many new techniques to integrate. So far, you've learned a few. You've learned substitution, and sometimes called use substitution. And you've seen the good, the bad, the ugly with that. We're now going to go to more advanced ways of doing integration. We're going to start with integration by parts. And we're going to start with the product rule. And the product rule, this is going to be maybe slightly different than the way you remember it. Is this here. And what I'm going to do is I'm going to knock that dx, I'm going to multiply all the way through by that. We're going to end up here. And what I can actually do, because it's a linear operation, I can actually integrate all three of those. So I'm going to add the integration symbol in front of all three. And if you remember, when you integrate d something, it just becomes that something. And what we're going to do is we're going to rearrange this a bit. And I'm actually going to subtract this one here. And then rewrite it as, and I'm going to write this one first. So the integral of f of x g prime of x dx equals f of x g of x minus the integral, and I'm going to rewrite that. I'm going to have the f prime of x next to the dx, just rearrange those. And then we're going to let u be f of x. Du is going to be f prime of x dx. We're going to let v be g of x. And dv is going to be g prime dx. And when we substitute all of that into here, we end up with our formula that looks like this. The integral of u dv equals uv minus the integral of v du. And we know there's a plus c. We'll get to all of that. Here is our new formula. And all I did was replace all of that into here. You can match that up yourself. Now, this can get a little overwhelming. So what we're going to end up with is this left integral here. That's going to be given to us. And we're going to have to figure out which part is the u and which part is the dv. The dv will always have the dx as part of it. There's a handy little acronym that we can use to know what we're going to let u be. So let's divide this off a little. So we're going to let u equal, and this is going to be our priority. First up is the I for inverse functions, inverse trig functions. Next up is L. So in other words, this is the orders, kind of like order of operations, where we start. Are there any inverse trig functions? That would be my U first. If not, next up we have logarithmic. Mostly that'll be the natural log of some sort, but we can certainly change the base and use the log of any base would work. Next up is the A, and that's algebraic. Which would be like your polynomials and things like that, which will apply here in just a moment. Next up is T. That's just for your straight up trig functions. And the last one you'll check is for exponential. So this is sort of the ordering. This is a good rule of thumb. LIATE or LIATE, or however you want to remember it, if you find that helpful and useful. And that is how we're going to figure out what U is going to be in our formula down here. And let's jump into an example. Example 1. Well, you'll notice in my piece here, my algebraic, my polynomials, is going to be my U before my trigonometry is going to be. So when we look at our first example like this, it looks to me like we were going to let U be X and dV is going to be sine X dx. Don't forget the infinitesimal. That's going to be part of it each time. Now you'll notice for my formula here, I don't just need U and dV, I need V and du. So all of them are being used in this case. So I can get du by doing the derivative. And I can get V by taking the integral. Again, don't worry about the constant of integration. We'll slap that on at the end. So this gives me a negative cosine X. And now it's just a matter of piecing together our formula. So we've identified our U and our dV. And you can see that X sine X dx is right there. That's everything. So we are now going to use the formula. I'm going to take U times V. So here we are, U times V. So that's going to give me a negative X cosine X minus the integral of V, which is right here, du, which in this case is dx. Now this becomes plus. And I know the integral of cosine is just plain old sine. If you're thinking, hey, what about the negative? That's when you take the derivative of cosine, you get that negative. The integral of cosine is still positive. And that is our first example of using integration by parts. It's not so bad once you figure out what U and dV is. All right, let's do another example. Now you'll notice in this one, I have a logarithm. And that one is definitely going to be it. Now you'll notice it's the only function here, so that might be a little confusing. What about the dV? Well, that actually is not a problem. Let U equal natural log of X. dV is going to be dx. And we'll have a couple of examples that work that way. Now to find du, a derivative of natural log is 1 over x dx. Don't forget the infinitesimal, the dx. And the integral of dv is v, and the integral of dx is x. So we have our u, which is ln. We have our dv, which is the dx. And now we have our 4 pieces that we need to do this. So using our formula, again, I'm using this formula. This is now going to equal u times v, so that's x ln of x minus the integral of v, which is x, du, which is 1 over x dx. Now you'll notice very nicely in this integral here, that just goes away. And the integral of dx, of course, is just x. Get your constant of integration. There we are. Now, I've seen some books write it like this. Let's see. So both would be considered correct. All right. Let's move on to a little bit more of an extreme version. Example 3. Now, you'll notice once again, if we look at our sheet, the polynomial or the algebraic are going to come before the exponential. So our u is going to be the t squared. I'm going to write this way up high here because we're going to have to actually do this whole process twice in this case, and you'll see why in a moment. So there's my u and my dv. Again, don't forget the dt. And du is 2t dt, and v is e to the t. So let's do one round of this. We're now going to get u times v, t squared e to the t, minus the integral of v e to the t, du, which is 2t dt. And you'll note, I'm going to rewrite this here. You'll note that the t squared that I had originally has dropped down to become a t. Well, what that means is I now have to do the entire process again. Let u be t, dv is e to the t dt, du is dt, and v is e to the t. So once again, I'm going to apply the process just to the integral here. Everything else is going to remain the same. T squared e to the t minus 2, and now we're going to do our process. U times v, that's t e to the t, minus the integral of v e to the t times du, which is dt. And we can see that this integral right here is very easy to do. And so when we rewrite the whole thing, and I'm going to distribute that -2 here. So it's negative times a negative gives me plus 2 e to the t, plus my arbitrary constant, of course. And so here we had to apply it twice. Now, you might be wondering, if that was t to the third, would I have to do it a third time? And the answer is yes, you would. All right. This next example is a little crazy. I keep saying that. And by the way, I have seen textbooks where they factor that e to the t out. So that would also be correct. That's not a wrong way of viewing that. All right. So in this case, if I go back to my list, here I have e to the x and sine x times sine x. You'll see trigonometric comes before the exponential. So I'm going to let u be the trig function, the sine x in this case. So let u equal sine x dv is the e to the x dx. du is going to be cosine x dx. V is just e to the x. And I'm going to write it like this. Integral e to the x sine x, that's what I started with, is going to equal u times v, minus the integral of v du. Okay, well, I'm going to actually apply this a second time. That was my first attempt. And we'll do this over here. Let u equal cosine x. dv is e to the x dx. du, negative sine x dx. And then v is e to the x again. We're going to do this whole process all over again, but just to this part here. That's still going to remain. Rewriting this for a reason. You'll notice I didn't write it with the other ones. All right, here we go. U times v. That's e to the x cosine x minus v du. Now the integral of v du, that's going to be a negative e to the x sine x dx. All right, so we have us a bona fide mess here. Now I'm going to point out that I have 1, 2, 3 negatives here. Minus e to the x cosine x. Now, again, that's going to give me overall minus the integral of e to the x sine x dx. Now, here's where things get weird. I'm going to notice I have this is the same as what I'm starting with. So now we're going to put algebra on overdrive, and I'm going to actually add this integral to both sides of the equation. We're considering them that they're like terms, as it were. So we now have 2 times the integral of e to the x sine x dx equals e to the x sine x minus e to the x cosine x. And now I'm going to divide both sides by 2. Giving us our answer. So the integral of e to the x sine x dx is going to be 1/2 e to the x sine x minus 1/2 e to the x cosine x plus our arbitrary constant. Now, many textbooks will factor out the 1/2 e to the x. That's a very common thing to do. But I'm going to leave it right here for our final answer on this one. You may need to rewind this recording and go through this again. It can be a little overwhelming. Not only are we doing it twice, but we have this whole subtracted to the other side thing. All right, and we are to our last problem for this video. What about a definite integral? No problem. For our definite integral, you'll notice, first of all, that we only have one function here. So that's going to be our inverse trig function. So that's going to be our u. Let's straighten that out. U be inverse tangent of x. dv is just going to be dx again. Now, if you remember, the derivative of inverse tangent is 1/1 plus x squared with our dx. and our v is going to just be x. Okay, so let's take our problem here and rewrite it as u times v minus the integral of v du. This is going to be x over 1 plus x squared dx. And of course, we are integrating this from 0 to 1. All right, I want to point out when I put, first of all, when I put 0 in there, those are both 0, so those are gone. So I only need to worry about 1. So this actually becomes 1 times the inverse tangent of 1. We'll come back to that. Now, you're going to note on this one, I have to use a second technique. I'm going to have to use substitution to do this one. Well, I'm not going to let u be something because I've already used u. So I'm going to let t equal 1 plus x squared, making dt equal to 2x dx. And I'll even rewrite it like this. And you'll note my x dx is right there. So this becomes the integral. Actually, I'm going to bring that 1/2 out in front. 1/2, the integral. We'll talk about the boundaries here in just a moment. Of 1 over t dt. So there's my 1/2. My dt is here. The x dx are replaced with the 1/2 dt. And this just becomes 1 over 1 plus x squared, and 1 plus x squared is t. Now the boundaries, they change. So when x equals 1, or 0, pardon me, t equals 1. And when x equals 1, 1 squared is 1 plus 1 is 2, t equals 2. Please note that the boundaries change as well. That's a very common mistake to make, is that you don't adjust the boundaries and you plug in to t values, you plug in the x values, the 0 and the 1. So just be extra careful there. Now, 1 times anything is itself, no problem. Inverse tangent of 1, if you recall, that's actually pi over 4. Once again, we are going from, in this case, 1 to 2. Good news is, natural log of 1 is 0, so I don't have to worry about that one. So this becomes pi over 4 minus 1/2 ln of 2. And that is my final answer. I hope that you found this helpful.